Hello again. So last time we discussed 8 basic features that characterize dynamic programming problem. To make these descriptions more concrete today, I want to show you an example. Distributing medical teams to countries. The example is about the World Health Council now has 5 medical teams available to allocate among 3 undeveloped countries to improve their medical care, health education, and 3 programs. The Council needs to determine how many teams to allocate to each of these countries, if any, to maximize the total effective of 5 teams. The teams must be kept intact, so the number allocated to each country must be integer. The measure of performance being used is additional person year of life. This table gives the estimated additional person year of life for each country for each possible allocation of medical team. For example, if give the first country 1 medical team, then 45 lifelong will be increased. So as the others. Now the question is, which allocation maximizes the measure of performance? To solve this problem, we first need to formulate the question. This problem requires making 3 interrelated decisions, namely how many medical teams to allocate to each of the 3 countries. Therefore, even though there is no fixed sequence, these 3 countries can be considered as the 3 stages in the dynamic programming formula. So, with that stage, there are 3 stages, N2, 1, 2, 3, 3 stages. And the decision variables are the number of teams to be allocated to stage means country N. The state here is the number of medical teams still available for allocation to remaining country. Okay. So according to this definition, so S1 here equals 5. We know there are total of 5 teams. 5 teams. S2, how many remaining? Is 5 minus X1. X1 means the number of teams to allocate to country 1. So if we allocate X1 teams to country 1, then the remaining teams will be 5 minus X1. The same to the state 3. It's the state 2. It's the state 2, which means number of remaining medical teams minus the teams allocated to country 2. Okay, the PIXI denote the decision effect. It's the measure of performance from allocating XI medical teams to country I. Its value is the table, in this table. In the table 10.1, the basic structure for the World Health Council problem is like this. In stage 1, the state is Sn. Then we shall decide how many teams shall allocate to the country n+1 to base on this performance measure. Okay. So the basic structure for the World Health Council problem, we use this to illustrate it. Then the recursive relationship. You know, we will solve the optimum problem, use the recursive relationship. That is, the optimal performance from n to 1 to the end, plus the decision performance of n, stage n, and give the boundary. There are only three countries, so the last stage is 4. Stage 4. Now, we're beginning with the last stage, n to 3, to solve the problem. We note that the value of P3, X3 are given in the last column of table 10.1. Therefore, with S3 medical teams still available for allocation to country 3, the maximum of P3 and X3 is automatically achieved by allocating all S3 teams. So, the optimal decision is this. This is the remaining medical team, and this is the optimal decision. We show this in this table. Then move back to start from the next to last stage, n equals 2. The alternative value of x2 now is 0, 1, 2, S2. We know that S2 is the medical team remaining in the start of stage 2. So we can use this formula to make the optimal decision. We can see that if S2 equals 0, then X2 can only be 0. Then S3 is also the 0. If S2 equals 1, then X2 can be 0 or be 1. You see that X2 is 0 to S2. There are two choices. And we can calculate the optimal performance using this formula. It equals the optimal performance in the stage 3 plus this stage's performance. So to make the performance maximize. Now come to if S2 equals 2, then X can be these three numbers, 0, 1, 2. This is the state of the stage 3. And we use the inclusive formulation to calculate its optimal solution. It's 70. If S2 be 3, also X2 can be 0 to 3 is S2, and left is the remaining medical team. It's 3, 2, 1, 0. Then we can use the incurve formulation to get the optimal solution. So go to the S2. If S2 is 4, then get X2 and the optimal. If S2 equals 5, then we get optimal is 160. Okay, move backward to stage 1. In this case, the only state to be considered in the stage 1 is 5. Then we can x1 equals 5. Then x1 can be 0 to 5. 0 to 5. It's the remaining. So we're using the formulation. We can get the optimal performance is 170. Okay, we put all the calculation table here, and we found that from here, in stage 1, we know that x1 is 1, x1 star is 1, which means that it is optimal to allocate one team to country 1. Then back to here, which makes x1 is 1, which makes s2 is 4. It's 4. Then we look this law. We can see that the optimal decision is 3, which means it is best to allocate 3 medical teams to country 2. Okay, then which leaves the how many teams for the third country is 3. Then the state 3, S3 will be 4 minus 3. There are only 1 team left. So we look at this law. The best decision or the optimal decision is that give the team to the third country. So the optimal solution is 131, which gives the objective function value to 170. This optimal solution means that 131 allocation of medical teams to the 3 countries will yield an estimated total of 170,000 additional person years of life, which is at least 5,000 more than any other allocation. Okay, now summarize the dynamic programming. From the example we illustrated, dynamic programming is a very useful technique for making a sequence of interrelated decisions. It requires formulating an appropriate recursive relationship. It is a very important step of this method to formulate an appropriate recursive relationship for each individual problem. However, it provides great computational saving over using exhaustive numerals to find the best combination of decisions, especially for large problems. For example, if a problem has 10 stages with 10 states and 10 possible decisions at each stage, the exhaustive enumerals must consider up to 10 billion combinations, whereas dynamic programming needs make no more than 1,000 calculations. Okay, that's all. Thank you.